Hi students, today we're going to look at chapter 3, dynamics. We're still going to look under the same category of the physics, classical mechanics. It means that the object that we observe and we study is relatively large and also the speed is relatively slow. Last week we looked into the kinematics. At that time, we didn't include the external force applied to it. Still, we study the object in terms of the motion, displacement, velocity, and acceleration. This week, we're going to look at the scenario when we apply a force and we check what is the new acceleration, velocity, or the displacement. Dynamics is subfield of the physics. It describes the motion when this object is under the act of the forces and causes the changes or the movement. Dynamics is established because we have the concepts laid down by Sir Isaac Newton many years ago. He says that the objects is governed by the law of the inertia that falls under the Newton's first law of the motion. Inside this law, it says that if we observe one object and that object is moving on the straight line, we're going to expect that this object will move in that same direction straight line forever unless there's external force applied to it. Same goes to the static scenario. If this object is in static, we're going to expect the object is static, not moving forever unless the external force applied to it. It's difficult for us to see this concept on the earth here because we have a lot of the air frictions and the surface friction. We can see this one in the outer space because there's consider like zero air friction. The second law of the motion, it is also called the law of the force. That is to find what is the relationship between the force and the motion. We can see the force when there are two or more objects, they are interact with each other and changes happen in terms of their motion. And Sir Isaac Newton, he found that when we apply a force from object 1 to object 2, we can see that the object 2 motion is described as ma. The mass of the object 2, a is the motion of that object 2, acceleration. When we apply a greater force, we're going to see that acceleration of the second object will become larger, faster. We go to the third law of the motion. This is also called as law of action reaction. It means that if I apply 100 Newton against the wall, oppositely 100 Newtons will apply back to me naturally. The magnitude the same, 100 Newton, only that the direction of the force is different. This is the book that written by Sir Isaac Newton. If you want to so-called observe the existing of the law of inertia, it's good that we see the events happen inside the outer space. If one astronaut is being pushed far away from the Earth, we're going to expect that this astronaut will non-stop flying further from the Earth in that straight line and forever. Second law of Newton, object 1, when he apply a certain force to the lawn, we can know the motion of the lawn by F equals to ma. M is the weight of the lawn, the grass cutter. A is the acceleration of the lawn. Third law, when we punch the wall will punch back to us. We cannot neglect that the existence of the hidden force, the force that doing something opposite back to us. For instance, one of the popular force is called the friction force. When we have two objects and they are touching each other, we can know so-called the hidden force by using this formula. The hidden force, friction force, equals to the coefficient of the friction times the normal force. Where can we find coefficient of the friction? We can check the table below. We need to identify object 1 is made of what material, object 2 made from what material, and then are they in static form or are they in the kinetics? There's movement between this object form. If let's say we know that the object 1 is the wood and object 2 is the snow, so if they are static, we're going to use this value 0.14, replace into this formula here. How about the N? N is the normal force. Let's say we have the surface is a bit slope here. This is the earth, this is the slope. There is the object here. This is the wood, and let's say this is the snow surface. The N is defined as this direction, going up. 90-degree perpendicular to the surface. This is the N. So the N later on we can find by identifying what is the gravitative force pulling down. So we can use the sine or the cos to dissolve it into the normal direction. Let's solve one problem. We have a skier, and then the weight of the skier total is 60 kilogram here. We are given the gravity is pulling down at 9.8 meter second square here. We want to find what is the acceleration of the skier at this direction. Let us use the purple color to indicate. We want to find what is the acceleration at this direction. We want to find the acceleration in this direction here. The direction is 25 degrees above the horizontal line here. We have three cases. The first case is the ideal case, means that there's no friction. The second case is we are given the number of the friction. The third case is a little bit complicated because we're just given the coefficient. What is the coefficient of the either kinetic or the static friction? Okay, for the first case, when we ask the skier, what do you feel the force right now? The skier will say that, oh, I did nothing now. I just feel the gravity force pulling me now. So the gravity force pulling him down is the total force. The forces that exist in the system. The force of the gravity, we can use the formula F equals to the F the gravity mg equals to 60 is the weight of the skier times the gravity acceleration is 9.8. So when we put into the calculator, we will get the number of 60 times 9.8, 588. This is the only force that apply to the skier. So same goes to the second skier, 588. Because these three cases, you feel that the only starting force is the gravity force. Now, we want to know what is the acceleration at the purple color direction. Here, we want to know the acceleration of the purple color direction. If we can know what is the force at the purple color direction here, then later on we can use the formula to relate them together. We have the only force, but it's not at the 25-degree purple color direction. Means that we need to use the sine of cos to dissolve the only force. The only force is the gravity force. Here. 588. So we need to dissolve it to this direction. Since 25 degree here, so we have balance of 65 degree here. To find the purple force, F equals to the 588 times the, we use the cos 65. 588 times cos 65, we'll get the value of 248.5. It means that when we ask the skier, okay, do you know what's the force that you are heading down at that 25 degree? He'll say that, oh, I can feel the 248.5, the force. We are not interested to know what's the force. We want to know what is the acceleration. So we use the relationship between the force equals to the MA, 248.5 equals to the M is the weight, A is the purple color direction acceleration, divide by 60. So we get the A equals to 4.14. So we solve for the A. We got A. Then we look at the B case. So for the B case, the total force felt by the skier is still the same, 588 newtons because of the gravity. When we dissolve at the interested direction, that is the 25 degree purple color, the force still the same, 248.5. This time, the skier said that, hey, wait for a while, I feel the 45 Newton against me. Means that the new force now is 248.5 minus 45 of the friction force. Where can we get 45? It is from the question here, 45. We expect to have a lesser net force to the 25 degree. So later on, the net force is 203.5. Again, we're going to use the general formula to find what is the acceleration. 203.5 minus, equals to, the weight is 60 kilogram. A is the new, the B case. 203.5, we divide by 60 kilogram, so we get 3.39. For the second case, acceleration is slower. How about the third case? We have the coefficient of kinetic friction given is 0.4. For this case, we need to find what is our friction force using the formula. F equals to the mu times the N. Okay, F we don't know, small f we don't know, but we have the mu. Mu is the 0.4 here. N is the normal force. Normal force is the 90 degree, referring to the surface. So for this case, we can use the gravity force 588 times the cos 25. Or easier, we can use the sine 65. Same. So 588 times sine 65, we get 532.9 Newton. Means that there is a 532.9 Newton against him. Let me check. I think there's some mistake here. Okay. 0.4 times 588 times sine 65. Sorry. After my calculation, I calculate wrongly. Supposed to be 213.2 Newton. Okay, sorry. Not so huge. So after the calculation using this formula, to find the friction. That is a total of 213.2 Newton against the skier. How about the net force? When we ask the skier, from the beginning, if everything is ideal, you have 248.5. But now there's a friction force against you. So how much do you feel the force right now? So we take these two numbers. The skier will say that I just have 35.2 Newton I felt. So equals to the MA, and we have 60 grams. So we can find the A equals to 0.59, same as this one here. Now let us look at another concept. It is called the momentum. We're going to answer one question: who is scarier? Before that, we want to define the momentum for our context. We are not looking about the circular momentum. We just want to know about the linear momentum. That is the straight line momentum. Momentum is defined as P, the momentum, equals to the mv. M is the weight of the object. V is the velocity of that object. When we say that there's a big momentum, the value is very big. It means that the object we are encounter is harder to be stopped. Who is scarier? If we ask Superman, Superman, do you rather to stop a mosquito or a Viva car here? When we use the formula to identify what is the value of momentum, the weight of the mosquito is so small and the speed of the mosquito is also small. When we want to find how hard to stop the mosquito, we times these two properties, we get the number here, a very, very small number. Let's look at the Viva car. The car is 755 kilograms, very heavy compared to the mosquito. And the speed per second of the Viva car, let's say it is driving at 90 km per hour, is 225 meters a second. We want to know how hard to stop the Viva car. This is the value of the momentum we obtained, 18,000, 19,000, somewhere there. When we compare these two, I guess that Superman will prefer to stop the mosquito because the number is very small, easy to be stopped. Okay, it's difficult to move to the next slide. When we say about the momentum will never disappear. It's like the energy. When we have a closed system, the energy value, the joule, will always be the same. It only can transfer the form from the, let's say, kinetic energy, it turns into the light energy, or it turns into the sound energy. For the momentum, it will be preserved. It means that the momentum before the collision will equals to the after collision. So we're going to write that momentum before equals to momentum after. M1 V1 equals to the M2 V2. Let's look at one example here. We have a yellow color ball that is 10 kilograms, and then we have a brown color ball B. That's also same, 10 kilograms. The before is the yellow ball is moving at 3 meters a second. We use the U to represent the initial velocity. The ball B is static, 0 meters a second. Then after the collision, the ball A moved at 45 degrees to the top, and the ball B moved 45 degrees to the below. When we look at the after incident, and they are moving at the same direction, we can say that both of these yellow and brown ball, A and B ball, we're going to have the same magnitude, the same value of the velocity. Okay, let us, using the conservation of the momentum to solve the problem. It says that the before collision momentum will same as the after. Only that for this case difficult because there's angle 45 degree. To solve this problem, we need to calculate based on their direction. We choose the horizontal to study for this momentum equality here. So later on, we're going to dissolve it to get the actual velocity that we want 45. So at this time, everything horizontally. Okay, so we ask the ball, what is your weight horizontally? The ball will say that I never change. Even if 30 degree, 45 degree, I am the same, 10 kilograms. So we have that. And the initial velocity of the ball is also horizontal, 3. Plus, the ball B is 10 kilograms. Here, ball B is 10 kilograms. And then it's static. It's not moving, 0. We go to the right-hand side expression there. The weight of the ball A is still 10, even though we consider it horizontally, same ball. Now, we want to find the velocity of the ball A horizontally. So we need to find ways to relate it to the this 45 degree, which is what we are interested. Okay, for this one, because at the end, the actual movement of the ball is going to the 45 degree. This is the real velocity. This is the dissolved unreal velocity. So to find what is the unreal velocity, so cos 45 degree will equals to the velocity vertically, horizontally, AH, divided by the VA. Then we're going to make VAH is the subject, will equals to VA times cos 45. Go back to just now assumption that since it's 45 degree, both means that the VBH will also same value as the VAH here. Okay, so VAH has another name. It's called the VA cos 45 plus ball B, the weight is still the same. And to reduce complexity, let's look at the equation here. So this will be 30, will be 20 times VA cos 45 degree. So we have a equation that is only consists of one unknown VA. So later on we can calculate and obtain our VA is 2.1 meter a second. Means that the velocity that we are interested to know is this direction, and the value is VA 2.1 meter a second. Same goes to the VB, because VB is equals to VA is 2.1 meter a second. Okay, there will be 3 questions given to you inside the tutorial chapter 3. After you solve the problem, remember to also upload your calculation. Yeah. So 3 questions plus 1 upload your calculation. Yeah. Okay, that will be all for this week. Take care and bye bye.